Hello. So far we have been discussing about free electrons, but most of the electrons in a solid cannot be absolutely free. They are at least subjected to a weak periodic potential, the potential having the periodicity same as the periodicity of the lattice. So let's try to understand what is the minimum that we can understand about the electronic states subject to a periodic potential. So let's start with one-dimensional case so that our mathematics and our understanding becomes easier, and then we will move on to more complicated situations. So let's start discussing a one-dimensional periodic potential and electron under the influence of that kind of a potential. So if we consider an electron in a one-dimensional potential, and if we express that potential as Vx, then the corresponding Schrödinger equation would be minus h cross squared over twice m d2 psi, which is a wave function of the electron and it's a function of x, dx2 plus Vx psi x equals energy eigenvalue E times psi x. Now the solution for Schrödinger equation is known for free electrons, for which the potential is always 0, harmonic oscillators, for which the potential is given as half kx squared, and uniform electric field. For which the solution, the potential is expressed as Vx equals electronic charge, protons charge times the electric field times x. This is not the energy, this is the electric field E here. So for these kind of systems, the solution to the Schrödinger equation is known. But here we have certainly a potential of different kind. We have a periodic potential. It's not very strong, but it has the periodicity of the lattice. We don't know exactly what the potential is. The potential would be different for different kind of systems, but the exact potential we are not interested in at this stage. We are interested in what we can qualitatively understand even without knowing the exact form of the potential, but knowing the fact that the potential is periodic in the periodicity of the lattice. So Vx in this context is a periodic potential, and if we have a crystal with lattice constant A, then the potential is also periodic in A. That means we can write Vx in this case equals Vx plus Ma. What is M? M is any arbitrary integer. This kind of a periodicity is there in the potential. So, the Fourier transform of a periodic potential Vx that can include only plane waves, and the wave number for the Fourier expansion can be given as Hn equals n times twice pi over A. Now, if we express this potential Vx in terms of a Fourier series, we can write Vx as sum over n equals minus infinity to plus infinity Vn e power I Hn x, and in general, if we have Vx not to be periodic, we can still have a continuum, we can have a continuous Fourier transform, but when Vx is periodic, it's a discrete Fourier transform with discrete Fourier coefficients. Otherwise, we will have a continuous Fourier coefficients that can be expressed in terms of integrals. Anyway, so if we start with no potential, that means free electron kind of a system. If we start with this Vx equals 0, then the wave functions in the Fourier expansion Wkx, these are just plane waves normalized to arbitrary length of the lattice e power I k x. The normalization condition has been chosen so that this wave function Wkx is normalized within the lattice, within the interval 0 less than x less than L. Now, the wave number k, these are real, and the energy eigenvalues are given as h cross squared k squared over twice m that we have learned so far. The plane waves make a complete set of orthonormal function that can be used for expansion of any wave function. So, it can be used as a basis set. Now, let us consider the eigenvalue problem when the potential is periodic but not 0. So, we have a periodic potential that can be expressed in Fourier series as sum over n equals minus infinity to plus infinity Vn e power I Hn x. We have, let us say, this kind of a periodic potential at hand. And now, if we consider the Hamiltonian operator as H equals p squared over twice m plus Vx, if we apply this operator to the plane wave, then what do we get? H applied on Wk x, this quantity belongs to, let's say, a subspace Sk. What kind of a subspace is that? This subspace is a subspace of plane waves. They have wave numbers k plus hn. We have the definition of hn in such a way that this subspace can be given as this set of Wk x, Wk plus h for n equals 1, x, h1, let's write Wk minus h1 x, Wk plus h2 x, Wk minus h2 x, and so on. So please go through this idea of subspace and what we are doing here a few times so that you understand it properly. Now we can see that the subspace Sk that we have chosen here, it's closed under the application of the Hamiltonian operator. That means if we apply the Hamiltonian on one of its elements, we will get another element within this set. We will get whatever element that is within this set. We won't get it outside this set. So diagonalization of the Hamiltonian operator within the given subspace Sk provides rigorous eigenfunctions of the Hamiltonian operator, and we can label the eigenfunctions of the Hamiltonian operator as psi k x. So now if we consider another wave number k prime, the corresponding subspace would be Sk prime. Sk prime is different from Sk, it's not related to Sk, it will have completely different elements, provided k and k prime, these are not related by integer multiples of twice pi over a. So Sk and Sk prime are different if k prime is not equal to n times twice pi over a plus minus k. If this condition holds, then these two subspaces are different. Now on the contrary, if we consider that k is, if instead of not equals to, if we put equal sign here, that means if we consider k equals k prime plus n twice pi over a, minus sign can be absorbed within n could be positive or negative integer, then this implies that Sk and Sk prime, they coincide. You can easily see by inspecting the elements in this set. Now, this fact that they coincide allows us to define a fundamental region in the K space. Which is minus pi over a less than k less than equals pi over a. This is the fundamental region. If you go beyond this, you will just repeat the properties that are found in this region. You won't get anything new outside this region. Therefore, this is the fundamental region. And this region includes all the different k levels, giving independent Sk subspaces. So, this fundamental region is, as you can see, of length twice pi over a, and this is called the first Brillouin zone or the Brillouin zone. If we consider a generic wave function psi kx that is obtained by diagonalization of the Hamiltonian in the subspace Sk. So, this wave function can be expressed as an appropriate linear combination of the plane waves. So, what kind of plane waves, what kind of linear combination can express a generic wave function in this subspace? Sum over n Cnk, these are the coefficients of the plane waves, then the normalization constant 1 over square root of L e power I k plus hn x. This is the expansion for any generic wave function psi k x. Now, it is convenient to introduce a new function ukx, which gives us sum over n Cn k 1 over square root of L, the normalization constant, e power I hn x. So, this k part is not included in uk, this one ukx. This hn part is taken here, which is nothing but, can be written in a bit different form, sum over n Cn k 1 over square root of L e power I n twice pi over a times x, putting the form of hn here. So, it is clear that this function ukx is a function with the same periodicity of the potential. You can see that from here, if x becomes a or integer multiple of a, it will show you clearly what the value becomes. It will go back to the same value. So, it is a periodic function with the same periodicity of the potential, that is of the lattice. Now, if we have defined this quantity, then we can write this generic wave function of that electron under the influence of a periodic potential as e power I k x times u k x. This kind of a form we can derive out of these analysis. Now, ukx, if we take ukx plus a, that is equal to ukx because uk is periodic in A. So, this expression here is called the Bloch theorem. This holds for the wave function of an electron subject to periodic potential. So, what is the statement? We can see that the generic wave function of an electron subject to a periodic potential can be expressed as an exponential function e power I k x multiplied by a function that is periodic in the lattice. It has the same periodicity of the lattice. Let us express the Bloch theorem in words because it is very important. Let us write it down. Soon we will see how powerful this theorem is. Any physically acceptable solution of the Schrödinger equation in a periodic potential takes the form of a travelling plane wave modulated on the microscopic scale by an appropriate function with the lattice periodicity. So, what is the travelling plane wave? It is the e power I k x, that part, that is the travelling plane wave, and u k x is the appropriate function with the lattice periodicity. This is the Bloch theorem. We can also state it in an alternative form. We can write that psi k with the argument x plus T n as e power I k T n psi k x, where T n is n times the lattice constant, where that is any translation in the direct lattice. So, the Bloch theorem guarantees the itinerant form of a wave function.